Hello everyone, I'm Irene. Welcome back to our openEuler OECA courses. In today's session, we are diving into an essential topic in operating system fundamentals, including system boot process, kernel boot process, and ways of managing boot processes. Whether you are a system administrator, a software engineer, or an enthusiast exploring openEuler internals, understanding how the system initializes and prepares itself for use is a critical skill. By the end of this course, you will grasp the overall boot flow of Linux operating systems, understand key components of the boot process, such as BIOS, UEFI, and GRUB, understand different methods to manage and customize the boot process. During Linux startup, the system initiates a power-on self-test post to verify the integrity of fundamental hardware components, such as the CPU, storage devices, and input peripherals. Upon successful completion, control is handed off to the firmware, typically BIOS or UEFI, which initializes hardware resources and scans for bootable devices. The firmware then locates the bootloader, generally GRUB or Grand Unified Bootloader, in the boot sector and passes execution to it. GRUB presents a boot menu for OS selection and proceeds to load the kernel image along with the associated init or init_tram_fs. Once loaded, the Linux kernel takes control, initializing key subsystems such as memory management, device drivers, and file systems. It then launches systemd, the first user space process, which orchestrates system initialization by mounting file systems, starting services, and activating defined units such as daemons, timers, and networking components. Linux supports two boot modes, Legacy BIOS or UEFI. To determine which mode the system is using, check for the presence of the /sys/firmware EFI directory. If this directory exists, the system is in UEFI mode. If it is absent, the system is using BIOS Legacy mode, as illustrated in the figures on the slide. Now let's explore the two primary boot modes used in Linux systems, Legacy BIOS and UEFI. BIOS, or Basic Input-Output System, is the first software that runs when the computer powers on. It performs post to check hardware integrity, initializes basic components like CPU, RAM, and storage, loads the bootloader from the MBR, offers a text-based setup utility for configuring system settings, and supports drives up to 2.2 terabytes. However, BIOS operates in 16-bit mode, lacking modern security enhancements. While BIOS served as the standard for decades, it has largely been superseded by UEFI due to its limitations. UEFI, or Unified Extensible Firmware Interface, is the modern successor to BIOS, designed to provide greater flexibility, scalability, and security. It supports 32-bit and 64-bit execution, enabling faster startup times. UEFI uses the GUID partition table, GPT, which allows booting from drives larger than 2 terabytes. It also includes features such as a secure boot to prevent unauthorized operating system launches and offers a graphical interface with mouse support. Although UEFI introduces new capabilities, its fundamental role remains the same as BIOS in the Linux boot process, loading the bootloader and transferring control to it. Next, let's explore MBR, a small but critical section located in the first sector of a storage device, typically a hard drive. The MBR occupies exactly 512 bytes and is divided into three key sections: a 446-byte bootloader, a 64-byte partition table, which records up to 4 primary partitions along with their sizes and locations, and a 2-byte magic number. Notably, the MBR is independent of any operating system. It can be freely read, modified, or deleted using low-level tools like the dd command. Regarding partitioning, a drive can contain up to 4 primary partitions, typically numbered from 1 to 4. If more partitions are needed, one of these can be designated as an extended partition, which acts as a container for multiple logical partitions. The layout and metadata of logical partitions reside within the extended partition itself. GUID partition table, or GPT, is another modern drive partitioning scheme. GPT uses 34 LBAs for partition metadata, the first of which is MBR compatible address, meaning it prevents legacy MBR-based utilities from mistakenly overriding GPT drives. LBA1 is the GPT header that stores the location and size of the partition table, location of backup partitions, and CRC checksums. LBAs 2 through 33 comprise the partition entry array. Each LBA can hold descriptors for 4 partitions, enabling support for up to 128 partitions in total. As illustrated above, both MBR and GPT are partitioning schemes used for organizing data on storage drives, but they differ significantly in structure and functionality. MBR represents stage 1 of the bootloader and resides in the very first sector of the bootable drive. GPT, on the other hand, employs a more robust design by using both primary and backup partition tables. These are stored respectively at the beginning and end of the drive. Unlike MBR, which references the sectors by physical sector numbers, GPT uses LBAs for locating partitions entries. For compatibility with the legacy systems, GPT drives retain the traditional MBR at LBA0, referred to as the protective MBR. Its purpose is to prevent legacy drive utilities that don't support GPT from misidentifying the drive and accidentally overriding its content. Following that, LBA1 contains the primary GPT header and the array of partition entries. Now let's see how to check which partitioning mode is used in your system. For openEuler, run the parted command. In the command output, a partition table type of MS-DOS indicates MBR mode, while GPT signifies GPT mode. In Windows, use the disk part utility to view drive details. If an asterisk appears in the GPT column, as shown in the slide, it confirms that UEFI boot mode is enabled. Both MBR and GPT partition styles are convertible. Before initiating the conversion, ensure the drive has at least 33 spare sectors available. For example, on the VDA drive, partitioning begins at sector 2048, which satisfies this requirement. In addition to running commands for conversion, this operation can also be performed via command line tools, interactive graphical interfaces, and third-party utilities with GUI support. So far, we've explored several system boot modes. Now let's take a closer look at how GRUB loads the kernel, another critical step in the startup sequence. When multiple kernels are installed on your system, GRUB presents a selection menu during boot. You can navigate through this menu to choose the desired kernel, as illustrated in the figure. Menu entries are defined in the GRUB configuration file, grub.cfg. This file also specifies kernel boot parameters, as well as kernel file and initRD file paths. You can see this more clearly in the current slide. The Linux command can specify the kernel file path and kernel boot parameters, and the initRD command to specify the initRD file path. Next, let's take a look at the system's default kernel. If you check the command output, you will see that this openEuler setup includes 2 kernel entries, one for the standard kernel and other for rescue mode. Now, by running the grub2 command, you can dig a bit deeper and figure out which kernel is actually being used. In this case, the default kernel is menu entry 0. Alright, now let's change the default kernel the system boots into. Before you run the grub2-set-default command, make sure the grub default in /extra default/grub is set to saved. That step's important, otherwise the change won't take effect. Then reboot the system to make the new setting take effect. Now, final part, let's check how to use System D to manage system boot services on Linux. Think of System D as a modern service manager. It works with older sysv and lsb initiation scripts, but adds a bunch of handy features. It can activate services through sockets or dbus, fire up daemons only when they are needed, restore system snapshots, and handle both mount and auto-mount points. One of its biggest strengths is how it fine-tunes the service startup logic, especially boot time parallelization. That means faster system startup by keeping unnecessary processes to a minimum and launching multiple services at once. To see what services are tied together during boot, just run the system control command. If there are no dependencies, like we see in the figure on the right, those services start up in parallel. To manage system boot services, let's start by checking if certain system services are set to run automatically when the system powers on. Take the rsyslog service as an example. If you run the command and see enabled in the output, it means the service is set to start on boot. If it says disabled, then it won't start up automatically. Now, if you want to change that behavior, either enable or disable it, just follow the commands shown here. Then run the cat command to see the service configuration file to check service dependencies. One key concept to understand in System D is the idea of a target. It basically replaces the old school run levels you might be familiar with. The cool part is you can build on top of an existing target by adding your own services, which lets you customize how your system boots. Take a look at the table here. It breaks down how traditional run levels map to System D targets and gives you a quick rundown of what each one does. Next up, let's check what your system's default target is. Just pop open the terminal and run system control space get-default. That will tell you what your system boots into by default. And if you are curious about all the variable targets on your system, you can run system control space list-units double hyphens type equals target. This gives you a full list of the active targets currently in play. Easy way to get the big picture of your system's boot behavior. If you are logged in as the root user, you've got full control to switch things up, whether it's the default boot target, the current one, or jumping into rescue or emergency mode. Just run the commands listed here and you are good to go. Just a heads up, if you are in emergency mode and want to get back to regular working mode, you will need to reboot the system. Well, this is the end of our openEuler OECA courses. You've explored core openEuler concepts, run powerful commands, and taken control of system behavior through targets, services, and more. You are now equipped not just use openEuler, but troubleshoot, customize, and optimize it for your needs. Again, thanks for joining the training. It's been a blast guiding you through it. Stay curious, stay sharp, and happy hacking.